Up till now, we have assumed that if we have a problem, let's say we have reactant A plus reactant B produces product C, and we've given you some specific amount, let's say 5 grams of A, we've assumed that reactant B existed in excess. But what if, instead of assuming that reactant B is in excess, we have a specific amount of reactant B and a specific amount of reactant A? Now, I'm not certain which one of those two reactants will run out, so I have to make that determination mathematically. We call that kind of problem a limiting reactant problem or a limiting reactant calculation, and here's how you recognize it. You're given a specific amount of more than one reactant. So at least 2 amounts of reactants will always be given in a limiting reactant calculation, and so you have to make the determination of which reactant is limiting. So here is a limiting component problem, which is similar to a limiting reactant problem. This time we're just making bicycles. And you're given 18 handlebars, 15 frames, and 20 tires, and assuming all other parts are available, what is the limiting reactant or limiting part in manufacturing bicycles? So here's how I recommend that you approach this. Well, if I'm going to make a typical bike, it's going to take one set of handlebars, and I'll just use HB for handlebars. It's going to take one bicycle frame, and I'm just going to use FR for frames, and it's going to take 2 tires, considering this is a bicycle, and that's going to make one bike. So this would be analogous to a chemical reaction that's balanced, and these are the coefficients for the manufacture of one of our product bikes here. So how do I determine which one of these components is limiting and how many bikes can I make? Well, I could simply plug in 18 handlebars here and work it out and see how many bikes I can make. It's a 1-to-1 ratio, so I should be able to make 18 bikes. But that's assuming that frames and tires exist in excess. On the other hand, I could assume handlebars and tires are in excess and just have 15 frames and do my calculation. Again, it's a 1-to-1 ratio, so in that case I could only make 15 bikes. So between handlebars and frames, 15 is definitely the limiting component. And what if I have 20 tires? Well, I want to know how many bikes can I make? Well, it takes 2 tires to make a bike, so that's a 2-to-1 ratio, and so I can only make 10 bikes if I have 20 tires and an unlimited amount of handlebars and frames, or 15 frames and 18 handlebars. So my limiting component is going to be tires. So let's take a look at how we might approach that. I actually have 2 methods for doing this. I'm going to show you the simplest method first. So let's take a look at what we've got. We've got 18 handlebars, 15 frames, and 20 tires. And so I want to know which one's limiting. Well, I can take, let's just say I take my handlebars, and I've got 18 handlebars. I'm just going to divide by its coefficient, and when I divide by the coefficient, I get 18. I'm going to do the same thing for frames. X frames. I'm going to go ahead and put my 15 frames over here. I'm going to divide by its coefficient, which is 1, which gives me 15. And then I'm going to do the same thing for tires. So this is X tires, and I've got 20 tires. which I'm going to divide by 2, its coefficient, and that gives me 10. So this is a really simple method. All you have to do now is look at the smallest number, and the smallest number is 10. That is going to be my limiting reactant. And so now I could go ahead and I could simply calculate how many bikes I could make with my limiting reactant, which is 20 tires. And it takes 2 tires for 1 bike. And so when I do the math, tires cancels. 20 times 1 divided by 2 is 10 bikes. And that tells me that 10 bikes are the most amount of bikes that I can make, and that tires is my limiting reactant or limiting part. Now, I could have gone ahead, done the problem 2 more times. X bikes, I've got 18 handlebars, and it takes 1 bike requires 1 handlebar. So that's a 1-to-1 ratio. When I cancel, handlebars cancels, I get 18 bikes. But I already know that if I only have 20 tires, I'm going to run out of tires before I get to 18 bikes. I'll run out of tires when I get to 10 bikes. And I could do the same thing with frames. How many bikes can I make if I have 15 frames? And it's again a 1 bike to 1 frame. And so when I multiply and divide across, frames cancels, and it gives me 15 bikes. So in all cases, I'm running out of tires before I get to 18 bikes or 15 bikes. I've run out of tires once I've gotten to 2 bikes. So the method is simply take the number of moles of your reactants, divide by the coefficient. Whichever one is smaller, that is your limiting reactant or your limiting component. The other method is go ahead and work the problem as many times as you need to go through all of your reactants that you're evaluating, but that's 3 times the work, or it's at least more work than the first method. Okay, so let's go ahead and try a real problem. A mixture of 0.80 moles of H2 and 0.75 moles of O2 are allowed to react. Which one is the limiting reactant? Well, we're going to use my method here. So we've got X moles of H2, and we're in moles, so we don't have to worry about it converting grams to moles. And we've got X moles of O2, and equal sign. So for H2, I've got 0.80 moles of H2. My coefficient for H2 is 2, and so I'm going to go ahead, I'm going to divide 0.8 by 2, which gives me 0.40 moles of H2. For the O2, I'm going to take my 0.75 moles of O2. I'm going to divide by its coefficient, which is understood to be 1, which gives me 0.75 moles of O2. All right, since I'm in moles here, all I had to do was divide by their respective coefficients for both of my reactants. Whichever one is smallest is my limiting reactant. Now, to figure out, so H2 is my limiting reactant, so how many moles of water are formed? Well, I can go ahead and calculate that real quick. X moles of H2O will equal 0.80 moles of H2. That's my limiting reactant. The coefficient for water is 2. So that's 2 moles of H2O, and my coefficient for H2 is also 2. So that's 2 moles of H2. When I do the math, moles of H2 will cancel. That's going to give me moles of water. So 0.8 times 2 divided by 2 is 0.80 moles of H2O. And that's all the water I can make, because my H2 is going to run out before I get to any more than 0.80 moles of water. Let's go ahead and prove that. So how about this? X moles of H2O. This time I'm going to choose as my limiting reactant my 0.75 moles of O2. My ratio for O2 is 2 moles of water to 1 mole of O2. Those are just the coefficients from the balanced chemical equation. This is my mole to mole ratio. So moles of O2 cancel, and I get 0.75 times 2 divided by 1, which is 1.50 moles of H2O. Well, the question is, can I make 1.50 moles of H2O if I only have 0.80 moles of H2? No, I ran out of H2 before I got to 1.50 moles of H2O, because H2 is my limiting reactant. So I'm going to ask one more question. I'm going to ask this question: how much or how many moles of O2 remain after the reaction? Now, we know that we're going to have some O2 left because it's the reactant that exists in excess. So what we need to do is we need to figure out how much we used and then simply subtract it from how much we started with. So how many moles of O2 get used in the reaction? And our limiting reactant, it's still the H2, which is 0.80 moles. And this is H2. And now my mole to mole ratio is between oxygen and hydrogen. I'm not concerned about the water. So I have 1 mole of O2 and 2 moles of H2. Okay? So here we go. 0.8 moles, H2, by the way, moles of H2 will cancel. So this will be 0.8 times 1 divided by 2. So I'm going to use 0.40 moles of O2. This is how much I used to completely consume my limiting reactant, which is H2. So how much is left? Well, since I used this much and I started with 0.75 moles, that's given in the problem, 0.75 moles of O2 initially, and then I just subtract. So I'm going to subtract the 0.4, and that's just going to give me 0.35 moles O2 remaining. Okay, so all I did to find out how many moles of O2 remaining, I calculated how many moles that I used using my limiting reactant H2, and then I subtracted however many moles of O2 that I used from how many I started with, and that gave me how many moles remained. This is a great problem. It's a great problem because you don't have a balanced chemical reaction, you don't have names for the compound or formulas for the compounds, and it's a limiting reactant gram to gram stoichiometry problem. So we're going to have to come up with everything and work this particular problem. Now, hydrogen sulfide, I'm not sure I would expect you to know this. It actually has a formula H2S. It's a binary compound. It's definitely an IDE. By rights, since it's a molecular compound, we should be calling it dihydrogen monosulfide, but nobody does. We just call it hydrogen sulfide. It is actually a gas. And we're going to bubble that into a solution of sodium hydroxide. Now, this one you should know. Okay, sodium hydroxide. Sodium is Na. Hydroxide is a polyatomic anion, OH. It's a -1 anion, a polyatomic anion, something you should know from the list, the first page of the list of polyatomic anions. Sodium is a group 1 alkali metal. These all oxidize to a +1 oxidation state, so that's a neutral compound. And what that's going to give us is a solution of sodium sulfide. This is an ionic compound, and it's between sodium and sulfur. Now, sulfur is a group 6 non-metal. That means it wants to collect 2 electrons to become a -2 sulfide anion. Sodium is an alkali metal +1 cation, so we need 2 of them. All right, and then the other product of this reaction is water, and I do expect you to know that that's good old H2O. All right, so here are, this is aqueous, by the way. It's dissolved in water. This is also aqueous. It's dissolved in water, and water is a pure liquid. These are all components of the reaction that you should be able to make a determination about. The only one that I might give you a pass on is hydrogen sulfide, because it's a common name that we use for dihydrogen monosulfide. So here we go. Let's go ahead and balance this guy. Well, let's balance the metals first. You know that technique. I've got 2 sodiums here, 1 here. So that's going to be 2 sodiums there. Let's go ahead and balance sulfur. I've got 1 sulfur here, 1 sulfur here. Sulfur appears to be happy. Let's check out the hydrogens. I've got 2 hydrogens plus 2 times 1. That's 2 hydrogens plus 2. That's 4. And so I need to change this coefficient to 2. 2 times 2 is 4. That gives me 2 oxygens, and then 2 times 1 is 2 oxygens. So this reaction is balanced. I have obeyed the law of conservation of mass. That is, mass has neither been created nor destroyed in a chemical reaction. The atoms have simply been rearranged, okay, using John Dalton's postulates. All right, so here we go. What they've given me is they've said I have 1.50 grams of hydrogen sulfide, so I've got 1.50 grams of this stuff, and I've got 1.85 grams of the sodium hydroxide. So the first thing I need to do is I need to convert grams to moles, all right? So I want to figure out how many moles of H2S that I have, and I want to figure out, and I'll put it over here, I want to figure out how many moles of sodium hydroxide that I have. And what I'm trying to determine, ladies and gentlemen, is which one of these reactants is the limiting reagent or limiting reactant in this particular problem. I have 1.50 grams of this stuff, and I have 1.85 0.85 grams of this stuff. Now, here's the deal. A lot of you are going to rush to say, well, I've got only 1.50 grams of the hydrogen sulfide. It must be the limiting reactant. Well, that may not be true, because sodium hydroxide may weigh more than the hydrogen sulfide. In fact, it does, which means that you're going to be dividing the larger number of grams by a larger denominator. That may give you a smaller number, and then you still wouldn't be sure until you divided by the respective coefficients. So let's go ahead and figure out what the molar mass of these two are. So the molar mass, if you haven't figured this out yet, is done by just using the periodic table of the elements. That's going to be 2 times 1.01. Sulfur on the periodic table is listed as 32.07 grams per mole, and we're going to put that up here. Sodium, we're going to do the molar mass of sodium hydroxide. Sodium is 22.99 plus oxygen, which is 16, plus hydrogen, which is 1.01. Now, I happen to know this works out very well to a nice round 40.00 grams per 1 mole. And hydrogen sulfide works out to 34.09 grams per mole. All right, so I'm going to go ahead and work that out in both particular cases. I've got 1.5 divided by 34.09, which gives me 0.0440. So that gives me 0.0440 moles. And over here for the sodium hydroxide, I have 1.85 divided by 40. And that gives me 0.0463 moles. So what are you thinking right now? Well, 0.440 moles is less than 0.463 moles of sodium hydroxide, so this must be the limiting reagent, right? No, you have forgotten that the coefficient of sodium hydroxide is 2 and the coefficient of hydrogen sulfide is just 1. So we're dividing this by 1 and we're dividing this by 2. So that's going to give us 0.0440 moles for H2S, and this is going to give us 0.0231. So here we've got 0.023, that's a 31 moles of sodium hydroxide. So by a good stretch, sodium hydroxide, this stuff right here, the larger amount in grams, this is our limiting reactant. So let's go ahead and figure out how many grams of sodium sulfide we can make. So X grams of Na2S equals 1.85 grams, and this is the sodium hydroxide. It's my limiting reactant. We're going to go ahead and divide by the molar mass, which is 40 grams per mole, grams for every 1 mole of NaOH. I need a mole to mole ratio. My X factor is the sodium sulfide. Its coefficient is understood to be 1, so that's 1 mole of Na2S. The coefficient of sodium hydroxide is 2, so that's 2 moles of NaOH. And when I multiply and divide across, grams of sodium hydroxide cancels, moles of sodium hydroxide cancels, and I have one more conversion. I need to convert moles of sodium sulfide, Na2S, to grams of sodium sulfide. And that's just multiplying by the molar mass of sodium sulfide. The molar mass of sodium sulfide will be 2 times 22.99 plus 32.07 for sulfur. I get 78.05 grams per mole. 78.05 grams for every 1 mole of sodium sulfide. When I multiply and divide across, moles of sodium sulfide cancels. Now keep in mind, we've done grams to moles, divide by the molar mass. We have the mole to mole ratio, which we got from the coefficients of the balanced chemical equation, and then we have moles to grams. And we got there by multiplying by the molar mass. Multiplying means it's in the numerator. Okay? Dividing means it's in the denominator. All right, let's see what we got. Grams of sodium sulfide, that's our X factor. Let's see what we got. When I do the math, which I'm just plugging this into my calculator, 1.85 times 1 divided by 40. I don't need to multiply times the 1. Just go straight to divide by 40 times 1, which you don't actually have to do because it doesn't change anything. Go straight to divide by 2 and then times 78.05. And you don't need to worry about dividing by 1. When I do that, I get 1.80 grams of sodium sulfide. So let's ask another question. How many grams of hydrogen sulfide, which is not our limiting reactant, this is the reactant that's in excess, how much remains after we've completely consumed 1.85 grams of sodium hydroxide, which is our limiting reactant? So let's figure out how much we use and then simply subtract it from how much we started with, just like we did in the last problem. So this is X grams of H2S used in the reaction. And so we'll start with our limiting reactant, 1.85 grams of sodium hydroxide. And we'll convert grams to moles of sodium hydroxide. This time the mole to mole ratio is between sodium hydroxide and H2S. Coefficient of sodium hydroxide is still 2. 2 moles of NaOH, and then 1 mole of H2S. And then 1 mole of H2S weighs how many grams? It weighs 3409. 34.09 grams. And we're figuring out how many grams of hydrogen sulfide that we used, completely consuming all of the limiting reactant, the sodium hydroxide. And so I'm just canceling units. We wind up with grams of hydrogen sulfide. So that becomes 1.85 divided by 40 divided by 2 times 34.09. And I plug that straight into my calculator. I'm not doing any smaller conversions. And so that gives me 0.788 grams of H2S used in this reaction. Well, how much do I have left over? Well, I started with 1.50 grams, And so I'm just going to do the subtraction. So that's going to be 1.5 minus 0.788. And that gives me 0. And since I only have 2 decimal places here, this is a subtraction that I'm doing. That's going to be 0.71 grams of H2S remaining. So that's a good problem, ladies and gentlemen. I recommend that you spend some time with it. Okay, I know this video is getting a little bit long, but we really only have one other concept and one other idea to work with. So let's press on. Let's finish Chapter 3 with this particular problem and this concept. All right, so let's take a look at this. I've got aluminum sulfide. Now, just to remind you, to get some use out of this, aluminum is a +3 ion. This is an ionic compound. Sulfur is a group 6A 2- anion in ionic compounds. That's going to be cross, and that's going to give you Al2S3 for that formula. So let's go ahead and plop that down right here. Al2S3. There's nothing wrong with this. It's empirical. You can't reduce it any further. And it reacts with water, which I know you know the formula for water, to form aluminum hydroxide. Let's do that one. Here's aluminum, which is +3. It's always +3. And here's hydroxide. Hydroxide is a -1 polyatomic anion. We're going to do our crisscross. Crisscross. This is telling me I only need one of these +3 aluminums, but I need 3 hydroxide ions. So that's going to give me Al. Since it's polyatomic, I have to put it in parentheses because I have more than one of them. If I only had one hydroxide there, like in sodium hydroxide, I wouldn't need to put the hydroxide in parentheses. But because I have 3 of them, more than one, I have to put the parentheses around the polyatomic anion and throw the 3 out there as a subscript, telling me I have 3 of these guys. Okay, I'm going to just go ahead and erase this guy. All right, so here we go. So that's going to form aluminum hydroxide and hydrogen sulfide, which we've already talked about. So here is our aluminum hydroxide and our hydrogen sulfide. Okay, so let's go ahead and balance this equation. Let's do the metals first. I've got 2 aluminums. Over here I only have 1 aluminum, so I'm going to change my coefficient to 2. Let's do sulfur. I have 3 sulfurs in the aluminum sulfide. I only have 1 here, so I'll change that to 3. And we just need to figure out what our coefficient of water is going to be. So let's go over here and look at hydrogens. I've got 2 times 3 times 1. That's 6 hydrogens. And then I have 3 times 2, which is 6 hydrogens. And 6 plus 6 is 12, so this needs to be a 6. And let's just check oxygen, make sure it's right. 6 times 1 is 6. And then I have 2 times 3 times 1, which is 6 oxygens. So we're balanced. We've obeyed the law of conservation of mass. We're in good shape. All right, so how many grams of aluminum hydroxide? So this is going to be how many grams of aluminum hydroxide are obtained from 6.75 grams of aluminum sulfide. So I have 6.75 grams of aluminum sulfide, and the assumption is that water is unlimited. So how many grams of aluminum hydroxide, AlOH3, and that's going to equal my 6.75 grams of Al2S3. Now this is not a limiting reactant problem because I have an unlimited amount of water, and this is my limiting reactant. Since this is gram to gram stoichiometry, I need to convert grams to moles. I do that by dividing by the molar mass, which is going to go down here. Then I've got my mole to mole ratio. So this is moles of Al2S3. This is moles of Al2S3. This will be moles of what I'm looking for, my X factor, which is aluminum hydroxide. And I'll just get that from the coefficients. I can go ahead and do that now. For aluminum sulfide, the coefficient is understood to be 1. For Al aluminum hydroxide, the coefficient is 2. And then this will be the last step. This is going to be moles to grams. So this is going to be moles of aluminum hydroxide, AlOH3, and this will be grams of Al parentheses OH3. All right, so anytime we're doing molar masses, this is always 1 mole, the mass of 1 mole. This is going to be the mass of 1 mole. All right, so let's make sure the units cancel. Grams of aluminum sulfide cancel. Moles of aluminum sulfide cancel. Moles of aluminum hydroxide cancel. And I wind up with grams of aluminum hydroxide. So I'm just going to plug this straight into the calculator. And it looks like this. I go 6.75 times 1 divided by 150.17 times 2 divided by 1 times 78.01. 7.01 grams of AlOH3. All right. Now, here's the deal. When these two reactants begin to react, as that reaction proceeds, I start running out of the aluminum sulfide. As I run out of the aluminum sulfide, it gradually gets to be a slower and slower reaction. It's based on something we call collision theory. And eventually, I reach a point where the reaction becomes balanced in a condition we know of as equilibrium. Not something you need to worry about. But the bottom line is this. I will get to a point where the production of aluminum hydroxide stops increasing. I stop getting more and more grams of aluminum hydroxide before all 6.75 grams of aluminum sulfide have completely reacted with the water. And so this yield that I get, what I've calculated here is what we call the theoretical yield. So it's theoretical in the sense that if all 6.75 grams of the aluminum sulfide completely reacted, theoretically, this is what I would get for aluminum hydroxide. But I never get there. I never quite get, even in a really good reaction, the entire theoretical yield. I get some fraction of the theoretical yield, some percent of the theoretical yield. So I get what we call an actual yield. And when I go in and I actually do the experiment, I'll get something less. So let's say I go into the lab, I take my 6.75 grams of aluminum sulfide, I react it with an unlimited amount of water, and I react and I react, and after a given amount of time, this is all I've got. And I'm thinking, well, I should be getting 7.01 grams. Well, that's only theoretically. This is the actual yield, which is always less. So the actual yield will always yield is always less than the theoretical yield. Than the theoretical yield. Okay? So what we want to do is we want to determine, well, how good is my reaction? How far did my reaction go? So what we do is we take that actual yield that I got from the experiment in the lab, and I divide it by what I calculated as my theoretical yield. So theoretical yields are always calculated yields. Actual yields are always experiment. So this is always experiment. This is always calculated. Okay, so you're always going to calculate the theoretical yield. You will be given, or you will go into the lab and you will determine the actual yield by experiment. And then you're going to multiply times 100 to get it into percent. So in this particular case, my actual yield was given as 6.50 grams. My theoretical yield, which I calculated, was 7.01 grams, and then I multiply times 100, and when I do that, 6.5 divided by 7.01, and I get 92.7%. That's a great yield, guys. So 92.7% yield. Okay. So, all you have to remember, actual over theoretical. All right, so let's just take a look at this slide. Percent yield, which you'll be called upon to calculate. Percent yield is just the actual yield. This is experimentally determined, and on an exam you have to be given this value because we don't expect you to go into the lab during an exam and actually run the experiment. So actual yield is the experimental yield, and the theoretical yield, that's what you calculate. Then you multiply times 100 to get it into percent. We're going to stop the video there. There's another problem on here, but I think we've covered this